Hello students, welcome to this lecture on problem solving session on atomic structure. You must have gone through the videos where we discussed the theory of atomic structure. We discussed several models of atom, and now in this class we would revise our content of this chapter, and then we'll see that how important insights we are getting, and we'll do this revision by the help of some selected problems. So let us start. The first problem here concerns the charge and mass of the subatomic particle. If you remember, we understood that the atomic model has the following structure. It has the core, the nucleus, which is at the core. The nucleus is composed of neutrons, which are neutral, and protons, which are positively charged, and surrounding this nucleus electrons go around in different orbits. So this is the picture of atom that we have in our mind, and now we also know what are the charge, what are the mass of these subatomic particles like electron or proton or neutron. The first question asks, calculate the mass and charge of 1 mole of electrons. So we know that mass of 1 electron is given over here, 9.11 into 10 to the power minus 31 kg, and this asks 1 mole of electron. So therefore the total mass of 1 mole of electron M equals 6.023 into 10 to the power 23, which is because there are in 1 mole of electrons you have this many number of electrons, and each electron has the mass of 9.11 into 10 to the power minus 31 kilogram. So therefore the mass of 1 mole of electron comes out to be 5.48 into 10 to the power minus 7 kilogram. Now this is the total mass of 1 mole of electron. Let us find out what is the charge of 1 mole of electron, and to do that we would again see we have 1 mole of electron. So 6.023 into 10 to the power 23, and we have now multiply the charge of this electron, which is, you remember know that it is a negatively charged particle. So therefore minus 1.602 into 10 to the power minus 19, the unit is coulomb. Now when you have when you do this, so this minus sign should remind you that this is the electron is a negatively charged particle, and when you do this number crunching you would get one important number, 96,485 coulomb, which is also has a common name, which is known as 1 Faraday. You would use this when you learn more about electrochemistry. So the 1 mole, so the charge on 1 mole of electron is 1 Faraday, or this number that you are having. So this is the first question. Now let us look at the second question. The second question tells, find the total number and the total mass of protons in 34 milligrams of ammonia. So let us call this A, and we look at the second problem here. The total number of protons and the total mass of protons in 34 milligram of ammonia. So if ammonia has 1 nitrogen atom and 3 hydrogen atoms, so therefore its atomic mass is 17 gram. So 17 gram of ammonia. So this is this this is a molecule. So therefore this is a molecular mass of ammonia. 17 gram of ammonia contains 1 mole of ammonia molecule, 6.023 into 10 to the power 23 number of ammonia molecules. So because this is its molecular mass. So now it says we have 34 milligrams. So let us find out how many molecules of ammonia will be there in 34 milligram of ammonia. So to get this, you will see 6.023 into 10 to the power 23 divided by 17, which is now gram. So therefore I am expressing it in terms of milligram, and in 34 milligram we will have this many number of ammonia molecules, and if you solve it, it should turn out to be, so this many number of ammonia molecules are present in 34 milligram of ammonia. But the question asks how many number of protons are there. Now, let us look at one molecule of ammonia. In one molecule of ammonia, nitrogen atom will have 7 protons. Each hydrogen will have 1 proton. So, therefore, together one molecule of ammonia has 10 protons, but in our sample of 34 milligram of ammonia, we have this many number of protons. So, therefore, 34 milligram of ammonia would have this number multiplied by 10. So, which is 1.2046 into 10 to the power 22 number of protons. Now, these many number of protons are present in 34 milligram of ammonia. We understood what is this, the first bit of this. The second bit says what is the total mass of proton, but we know what is the mass of one proton. So, this is given here. So, therefore, the total mass of protons in this sample, you would have 1.2046 into 10 to the power 22, these many number of protons, multiply that with 1.672 into 10 to the power minus 27 kilograms, and if you solve this, you would come about, you will get something about 20.1 milligram. So, you see that in 34 milligram of ammonia, we have 20.1 milligram of protons. So, the remaining mass is contributed by the neutrons, because you know that in an atom the electrons have very little mass. So, therefore, approximate mass in atomic unit it is 0. So, the proton and neutrons contribute to the mass of the nucleus. So, therefore, the 20 milligram of mass is coming from proton and the remaining mass will come from the neutrons. Okay. So, let us look at the next question. The next question concerns about the atomic mass and atomic number. Now, when we are discussing this chapter, you say we represented an atom in this particular form, where x would be the symbol of the atom, z is its number of protons, atomic number, and a is its atomic mass or mass number. So, this question, the first bit asks the atom that we have is 2656, find out how many neutrons and protons are there. So, when you see Z is 26, Z is that atomic number, which is also the number of protons. So, number of protons. So, you immediately know by looking at this value. So, number of protons are 26, but its mass number is 56. The mass number is number of protons plus number of neutrons. So, since 26 is the number of protons, so therefore, number of neutrons is 30. Number of neutrons is 30. So, we got this question. This has 26 number of protons and 30 number of neutrons. Now, let us look at another question which also uses the similar concept. This says that you have an ion whose mass number is 37. So, let us write down. So, the A is 37, that is, it possesses 1 unit of negative charge. When an atom has 1 unit of negative charge, we call it an anion, and it happens because it has got 1 electron extra than what it has as the number of protons. So, therefore, number of electron in this atom is number of proton plus 1, then only charge of minus 1 occurs. If you have a cation or positive charge, that means number of protons are greater than number of electrons. So, this is what we have, Ne equals Np plus 1, because this is an anion with an unit 1 unit of negative charge. It also tells the ion contains 11.1% more neutrons than the electrons. So, that means number of neutrons is 11.1% more than number of electrons. To write that, I can write simply, if I have one number of electron, then if I have one number of electron, the number of neutrons is 1.111, because this is 11.1% greater than the number of electrons. So, therefore, this value is the number of neutrons. Now, atomic mass is given 37. How do I get this atomic mass? If I add n number of neutrons to number of protons, that means Np plus Nn is 37, but I know Np is Ne minus 1 and Nn is 1.111 Ne. So, this is equal to 37. So, this minus 1 goes the other side. So, I have, and therefore, number of electrons becomes 38 divided by 2.111, which is, if you do it, you will get 18. So, that means it has got 18 number of electrons. So, what is the number of protons? Number of proton is 1 less than number of electron. So, therefore, number of proton is 17, and if number of proton is 17, so that means this is Z is 17, and Z 17 means we know that this is chlorine, the species is chlorine. And what is number of neutrons? Number of neutrons is A minus Z, which is equivalent to 20. So, therefore, the Z is 17, A is 37, this is the atomic number, this is the mass number, and the atom that you, by looking at Z, you know that this is chlorine, but this is not just chlorine, this is actually chloride ion, because you have one negative charge. So, the question asks find the symbol of the ion. The symbol of the ion is here, this is Z, this is A, and this is the number of charges present in this atom. Okay. So, we go ahead and we will look at the next question. The next question concerns about the wavelength, wave number, frequency and time period and of a wave, and how they are related to the energy of this wave. So, we saw that interaction of radiation with matter. We talked about photon. Photon has both a wave like nature and a particle like nature, and what is the energy of the photon. So, the expressions that are useful in this discussion are summarized here. So, we discussed that if we have a radiation with frequency nu, then the energy associated with that radiation is E given by h nu, where h is the Planck's constant, which is a universal constant. Nu, which is the frequency, can also be expressed in terms of the wavelength c by lambda, where c is the speed of light. It can also be expressed in terms of wave numbers, nu bar as c into nu bar. So, where nu bar is simply 1 over lambda, and this is also, it can be expressed in terms of the period of this wave. So, let us look at this question. The question says, the first one, find the energy of the photon which corresponds to the light of frequency 3.10 to the power 15 hertz. So, we see that the question gives us nu equals 3 into 10 to the power 15 hertz, which is also second inverse. So, what is the energy? So, we know that E is simply h nu, where h is the Planck's constant, 6.626 into 10 to the power minus 34 joule into second, and multiply that with the frequency, which is 3 into 10 to the power 15 hertz is second inverse. So, when you do this multiplication, you will get 19.88 into 10 to the power minus 19 joules. So, this many joules is the energy corresponding to this photon. Of course, you can convert this into other units such as electron volt. Now, this is the first bit of the question. The second, if the photon has wavelength of 0.5. So, in this question, instead of giving nu, the problem gives us the wavelength, which is lambda, 0.5 angstrom. We know that 1 angstrom is 10 to the power minus 10 meter. So, therefore, this I can express in terms of meter unit, and this is 5 into 10 to the power minus 11 meter. Now, what will be the energy? Energy is simply E hc by lambda, this one. Now, I have two constants to worry about. 6 is the Planck's constant multiplied by 3 into 10 to the power 8 joule second meter second inverse. Joule second is the unit of Planck's constant, meter per second is the unit of the speed of light, and divided by the wavelength of the radiation, which is given in the unit of meter. Second inverse cancel out, meter cancel out, and I am left with joules, which is actually the correct unit of energy. So, I can see this if you do the numbers, you would get 3.976 into 10 to the power minus 15 joules. So, this is the energy of. So, if we know the frequency or the wavelength of the light or a photon, we can convert them to energy, or vice the other way around also. So, now let us look at the second question. The second question does not ask to convert them to energy, but it asks if there is find the wavelength of the photon whose period is 2 into 10 to the power minus 10 second. So, the time period tau is 2 into 10 to the power minus 10 second, but we know tau is closely related to the frequency. So, therefore, frequency is 1 over tau, which is 0.5 into 10 to the power 10 second inverse or hertz. This is the frequency. Now, the question asks wavelength, but we know that nu is c by lambda. So, therefore, lambda is c by nu. So, to get this, so 3 into 10 to the power 8 meter second inverse, that is the speed of light, divided by the frequency, which is now 0.5 into 10 to the power 10 second inverse. So, you would see that the unit that would come out will be in the unit of meter, and this comes out to be 0.06 meter. Of course, if you want, you have here lambda, you can also convert it to nu bar, because this is simply 1 over lambda, and then you will get the number in the units of meter inverse, which is the wave number. So, the point that you should remember here is that there are various ways to express a wave, either through its wavelength or time period or a wave number, but they are all interconvertible and they correspond to one energy associated with one energy, which is given by, if we multiply them with the Planck's constant h. Okay. Now, let us look at another question. This question concerns photoelectric effect. If you remember, the discussion that we had on photoelectric effect is that if we irradiate some light onto a metal surface, then a light, when you have light of frequency nu is used, then the energy associated with this light is given by E as h nu, and when you shine this light on metal surface, then at some point of time you would see that the metal would start losing electrons, and that you can, of course, when you connect them to a circuit, then you can experimentally observe them. So, every metal, we understood, that is associated with its characteristic value of work function, which is phi 0, whose energy can also be converted to the frequency through Planck's constant. Now, if I am irradiating a light with h nu frequency, the metal has work function of phi 0. After compensating the metal with its work function, whatever energy remaining will be used as the kinetic energy of the ejected electron. So, that means the energy associated with phi 0 plus the kinetic energy of the electron will be equal to the energy of the radiation that we are using. So, this is about the photoelectric effect. Let us look at the question. The question says that we have a photon of wavelength 4 into 10 to the power minus 7 meter. So, therefore, lambda is given 4 into 10 to the power minus 7 meter. It strikes on the metal surface, and the work function of the metal is phi 0 is given as 2.13 electron volt, and we have to calculate the energy of the photon, kinetic energy of the emission, and the velocity of the electron. So, first let us look at the first bit, the energy of the photon. So, energy of the photon E is hc by lambda. So, you see that we are often using the multiplication of these two constant hc, 10 to the power minus 34 into 3 into 10 to the power 8 joule second meter second inverse. So, it is a good idea to actually remember the result of this product hc in joule a meter unit, so that you can directly use them and you will be faster to solve problems. So, this is the energy we already have used such an expression. When I do this, I would get 4.07 into 10 to the power minus 19 joule, but this is better if we can convert this energy into from units of joules to the units of electron. How do we do? We know that 1 electron volt is this many joules given here. So, to convert it to electron volt, so we have 4.07 into 10 to the power minus 19 divided by 1.602 into 10 to the power minus 19. This is in the unit of electron volt, which would come out to be 3.10 electron volt. This is the energy associated with the photon that we are giving. Now, looking at the second bit, we see it is asking what is the kinetic energy of the emission. So, this much light energy we are giving through the light, the work function is phi 0 given here. The remaining energy will be converted as the kinetic energy of the electron. So, kinetic energy of the electron is E minus phi 0, which is 0.97 electron volt, because phi 0 is 2.13 and this is 3.10 volt. So, this is the third bit asks what is the velocity of the photoelectron. So, this is kinetic energy. So, this is kinetic energy can be written as half mv square, which is 0.97 electron volt. Now, we can express it in terms of joules unit. So, this kinetic energy half mv square is given here. So, therefore, v square is 2 into m. What is m? M is the ejected the mass of the ejected electron. So, 9.11 into 10 to the power minus 31, forgive me, this has to be divided, not multiplied. 2 into 0.97, 1.602 10 to the power minus 19 joule divided by, this is 9.11 into 10 to the power minus 31 joule per kg. So, you know joule per kg will be meter square second inverse square. So, therefore, V is the square root of this. So, joule per kg I can write as meter square second s to the second to the power minus 2, and therefore, V will be obtained by taking the square root of this, and when you do this you will get 5.84 into 10 to the power 6 meters per second. So, this is the speed with which this ejected electron will go out. Come look at this speed, which is about close to 6,000 kilometer per second. So, that is quite a fast electron there. All right. So, we proceed to the next question. The next question concerns the hydrogen atoms energy levels. So, if you remember, we discussed the hydrogen atom emission problem through Bohr's model, and then we also saw that Bohr's model has some certain limitations, and then exact treatment of quantum mechanical treatment of hydrogen atom gave us proper results, which is given over here, which tells that the hydrogen atom's energy levels are discrete, they're quantized. So, we have the n, where n is the quantum number that goes from 1 to larger numbers. So, energy of the nth state of hydrogen atom is given by this expression, which is here is a constant, multiplied by z square divided by n square, where z is the atomic number of the system and n is the quantum number or the state. So, the ground state here n equals 1, the next one is n equals 2, n equals 3, n equals 4, and so on and so forth until very large number of n. So, now let us look at the question. What it tells? It tells what is the wavelength of the light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n equals 4 to an energy level of n equals 2. So, the electron goes from n equals 4 to n equals 2. So, this transition is happening. So, we see that when electron jumps from a higher orbit to lower orbit, it will emit some energy. So, it is asking what is the wavelength of that energy that the electron will emit. So, to answer that, we have to first know what is the energy of the fourth orbit. So, this is very easy. We simply have to take this constant, multiply with the atomic Z is 1 for hydrogen atom, N is 4 now. So, this is my 2.18 into 10 to the power minus 18 1 by 4 square. This is in the unit of joules. What is the energy of second level? N equals 2. This is again simple, 10 to the power minus 18, 1 over 2 square, again the unit of joule. So, when it happens, the jump happens, what is the energy of the emission? The emission energy is given by E final minus E initial. So, that you would get to 10 to the power minus 18, 1 by 4 minus 1 by 16. So, you would, when you do this, this will come out to be 3 divided by 16, and when you multiply this number, you would get this as minus 4.087 into 10 to the power minus 19. So, this is in the units of joules. So, this is this many joules. So, this is the emission energy. What is this minus sign doing here? This simply says that this is the energy that is being emitted, not observed. So, this minus sign indicates that. So, now corresponding to this energy, what is the wavelength? So, lambda we know we know energy is E by hc, E equals hc by lambda. So, therefore, lambda is hc by E. Again we have to deal with the multiplication of the two constant. Divided by 4.087 into 10 to the power minus 19 joule, which should come out to be in the unit of nanometer, it is 486.3 nanometer, which is 10 to the power minus 9 meter. So, this is the wavelength that the electron will emit when it jumps from n equals 4 to n equals 2. Now, let us look at the second bit. It says how much of energy is required to ionize hydrogen atom if the electron occupies n equals 4 level. So, that means my electron is here to begin with and I am ionizing it. What does it mean? When I ionize, I actually remove this electron from one finite value of n to a very large value of n, or I can say the final state has n equals infinite. That is the state of ionization, where the electron is completely detached from the nucleus. So, therefore, n goes very high and infinite. So, E infinite, or when n is very large, you would see that this 1 over n square or 1 over n square will make this term go 0. So, therefore, the final state here for ionization, the final state energy is simply 0. So, which is given here, this is the ionization limit, whose that means the electron is now called a free electron. It is not associated with any nucleus. So, its energy is 0 because n goes very large. And what is the E initial? E initial is simply E4. So, the ionization energy, what would be, how much you would do? To ionize this electron from n equals 4, you have to give the energy corresponding to this E4. So, you can see 0 minus E4, that would be simply the ionization energy would be 2.18 divided by 16 into 10 to the power minus 18 joule, which will turn out to be 1.36 into 10 to the power minus 19 joule. So, this is the ionization energy. It is simply the energy of that particular orbit from which you are ionizing the electron. Okay. So, let us look at the next question. The next question is something similar. We discussed hydrogen atom. The advantage of using quantum mechanical model instead of Bohr's model is that we can use this expression even for hydrogen like system. That means when we go to hydrogen like system means when Z is not necessarily 1, Z is greater than 1, but still the system has 1 electron. So, now let us look at this question. It tells you what is the energy required to do this following process. What is the process? It starts with He plus. If you recall what is helium. So, helium has got 2 electrons and its nucleus has 2 protons and 2 neutrons. So, this is helium with 2 electrons. How do I get helium plus? This reactant is helium plus. I will get this when I ionize 1 electron. So, therefore, the helium plus is given here. This is my helium plus with the nucleus which has Z equals 2 and 1 electron. So, this is a hydrogen like system. Now, what is the reaction? The reaction is I am removing this one electron that is there in He plus, so that I simply have the He2 plus a free electron. So, this electron has been ionized. So, now how much of energy do I need to carry out this ionization? So, to do that, I already know to carry out this ionization I need to know what is the energy of this state. What is the energy of this state? So, this is He plus with Z equals 2. So, the energy of the starting state is given by this relation minus 2.18 10 to the power minus 18. Here Z is the nuclear charge, which is 2. So, therefore, multiply it with 4, and N, since the system exists in this ground state. So, N equals 1 here. So, this is simply into 4. This is the energy that of the reactant. So, this would turn out to be 8.72 into 10 to the power minus 18 joules. So, this is the energy of He plus. When I remove this electron, to ionize this electron, I must give this energy. This negative sign indicates that the system He plus is a stable system. So, I must give 8.72 into 10 to the power minus 18 joules to ionize this electron. So, therefore, the energy required is this quantity shown here. Okay. So, the next question that we are going to discuss concerns the de Broglie's hypothesis. You remember to describe the black body radiation or photoelectric effect, we said that light, which was popularly known as a wave, also has particle like nature. But de Broglie suggested that not only a traditional wave has a particle like nature, but conventional particle also has a wave like nature. So, the wave particle duality became complete when we have de Broglie's hypothesis. So, de Broglie's hypothesis says that if you have a particle whose mass is m and moving with a speed of v, so its momentum is given by mv. So, corresponding to the wavelength corresponding to this particle lambda is given by h by p or h by mv. So, if we know the mass and velocity of a particle, then we can know its corresponding de Broglie's wavelength. So, this question concerns that. So, the mass of electron we know, its kinetic energy is given by this energy, calculate its wavelength. So, we know that kinetic energy is p square divided by 2m, which p is the momentum. So, this is given as 3 into 10 to the power minus 25 joules. So, therefore, p square is 2 into mass of electron 9.11 into 10 to the power minus 31 kilogram, 3 into 10 to the power minus 25 joule multiplied by joule kilogram. So, therefore, I will get p as the square root of this quantity, and the p that would come out to be is 7.39 into 10 to the power minus 28 with the unit of kilogram meter second inverse. So, now I got the momentum of this particle from the kinetic energy. If I know the kinetic energy, I got the momentum because I already know the mass of this particle. Now, I got the momentum, but what I need now is the de Broglie wavelength, which is given by h by p, and h is 6.626 into divided by the momentum, and when you do this, you would get 0.897 into 10 to the power minus 6 meter, which is about 897 nanometer. So, this is the de Broglie's wavelength. So, that means an electron whose kinetic energy is 3 into 10 to the power minus 25 joules is also a wave, and corresponding wavelength is 897 nanometer. Now, in this question, we will discuss about the solutions of the atomic model that we had. After doing quantum mechanical solution, we realized that the states of hydrogen atom and then we can generalize to other hydrogen like systems. States of this system depend on different quantum numbers. So, the 4 quantum numbers we discussed in our class. They are the principal quantum number, which goes from which is denoted by n, which goes from 1, 2, 3 and higher values. For each principal quantum number n, we have associated azimuthal quantum number, which is denoted by L, and the value of L goes from 0 to 0, 1, 2 to n minus 1. So, therefore, once we define n, we have an upper limit of L. Again, for each value of azimuthal quantum number, we have associated ml, or the magnetic quantum number, which goes from minus L to plus L in the step of 1. And apart from these 3 quantum numbers, we also have the electron which has a spin, and we denote the electron spin with the spin quantum number as ms equals plus half or ms equals minus half, signifying the up spin of the electron or down spin of the electron. This particular question concerns about this quantum number. For example, this question asks how many subshells are associated with n equals 4. So, to answer the first bit, so we know that we got this question that n equals 4. So, therefore, the principal quantum number n is given, n equals 4, and we know for n equals 4, L goes from 0 to n minus 1, and in this case 0, 1, 2, 3. So, these 4 are called subshells. So, these are the 4 subshells that we have. Now, for each value of L, we have ml values, 2L plus 1 number of ml values. Suppose L equals 0. So, therefore, since L is 0, 2L plus 1 is 1. So, therefore, one possible value of ml exists, and that value of ml is 0. And this one we call as an orbital. So, I have got one orbital. So, since n equals 4, L equals 0, ml equals 0. So, this orbital is 4s orbital. Similarly, when I go to L equals 1, I have 2L plus 1, that means 3 number of ml values. So, ml goes from minus 1 to 0 plus 1. So, therefore, I have 3 orbitals in this subshell. So, this can be 4p, and for L equals 2, I have ml equals plus minus 2 plus minus 1 0. So, therefore, 5 orbitals in this subshell, and L equals 3, I have ml value going from plus minus 3 plus minus 2 plus minus 1 0. So, therefore, 7 orbitals. So, 1 orbital for L equals 0, L equals 1, we have 3 orbitals, L equals 2, we have 5 orbitals, L equals 3, we have 7 orbitals. So, together we have got 1 plus 3 plus 5 plus 7, that is 16 orbitals. So, we have got 4 subshells, we have got 16 orbitals. So, this number of orbitals of course goes as n square. So, if n is 4, so we have n square number of 16 orbitals, and if number of subshells is also given as n, because it goes from 0 to n minus 1. So, therefore, if principal quantum number n is given, so you have n number of subshell, you have n square number of orbitals, and you know that each orbital can have 2 electrons. So, therefore, number of electrons will be 2n square, in this case it is 32. So, how is that possible? Because each orbital can contain 2 electrons over here. Similarly, I can fill 14 electrons here, 10 electrons here. So, if I fill all the 16 orbitals, I can fill with 32 electrons. Out of them, you see that in each orbital, one electron has spin ms equals plus half, the other one has ms equals minus half. So, one is alpha spin, another is beta spin, and that is happening in each orbital. So, since I have 16 orbitals, so therefore, I have 16 number of electrons that can have ms equals plus half, and the remaining 16 electrons will have ms equals minus half. This concerns the second bit of this question. The second bit of the question tells how many electrons are there in these subshells having ms value of minus half for n equals 4. So, you see that for n equals 4, we have 4 subshells, 16 orbitals and 32 electrons. Out of them, 16 or exactly half of these electrons can have ms equals minus half, and the remaining half will have ms equals plus half. So in this way you actually what you should learn in this problem is that each electron in this case has a specific identity. It has an identity with respect to the principal quantum number. In this case n is 4 for all these 32 electrons. They can have one of these 4 subshells 0, 1, 2, 3, 4s, 4p, 4d, 4f orbital subshells, and in each case 4p, 4s will have 1 orbital, 4p will have 4px, 4py, 4pz, 4d will have 5 orbitals, 4f will have 7 orbitals, and if I fill all the electrons, I can fill 32 electrons, out of which 16 will be up spin or the alpha spin, ms equals plus half. The remaining 16 will have beta electron, which will have ms equals minus half. So this question concerns about the quantum number of the quantum numbers of an electron. Now, after learning about these orbitals, we started to know how to we can arrange these electrons in different orbitals. So this question concerns that. So it says that an atom of an element contains 29 electrons and 35 neutrons. So this shows that this is not an ion, this is an atom. So therefore number of electrons is equal to number of protons. So it asks deduce the number of protons. So therefore we already know. So if it is an atom and not an ion, so it has 29 electrons. So therefore the number of protons is going to be 29. So if we know number of protons is 29, that means Z is 29. So we know which atom we are talking about. That is, this is copper. And it asks to find out the electronic configuration of this element. So this is copper. So this is 29, its Z value, A value is the mass number is 29 plus 35, that will be 64. We will have to find out the electronic configuration for this. To do this electronic configuration, you remember that we have to arrange the orbitals in their increasing order, and we get this increasing order by taking n plus L value. So we have 1s, then we will fill 2s, then we will fill 2p, then we will fill 3s, then we will fill 3p, then 4s, then 3d, 4p. So this diagram I am sure you are familiar with. Now this is the increasing order of n plus L that is given here. So let us write down 1s, 2s, 2p, 3s, 3s, 3p. So after 3p I will not write 3d, rather I will write 4s, because 4s will have n plus L. So 4s has n plus L 4, 3d has n plus L 5. So therefore this way. So let us try to fill the electrons from lower. So 1s can have 2 electrons. So I already gave 2 electrons to them. So 2s and 2p can have 2s can have 2 electrons, 2p can have 6 electrons. So together now if I count, I have already used 10 electrons. Now let us look at 3s and 3p. So if I fill 3s 2 3p 6, I am done with 18 electrons. So I am left with 11 more, because I have got 29 electrons to fill. So I have 4s, I give 2 electrons, I have 3d, I have, so after giving 2 electrons I am done with 20 electrons. So therefore I am left with 9 electrons. Let me fill these 4 into 2 8 and 1 over here. So this configuration turns out as 4s2 3d 9. But there is a problem with this configuration, is that this shell, this subshell 4s is fully filled, but 3d9 is just next to fully filled. So if we know that half filled and full filled shells are the most stable ones. So they can have an internal arrangement, so that you have 4s1 and 3d10, such that this is half filled, therefore provides stability. This is fully filled, so therefore this also provides stability. So therefore with 29 electron you have 4s1 3d10 electronic configuration at the valence, and then you have these core orbitals which are given here. So this is the electronic configuration of this element. Now the next question concerns the orbital shapes, or in particular it wants to find out how many nodes are there in these orbitals. So you remember when we have different L values as azimuthal quantum number, so we have s orbital or p orbital or d orbital. We know s orbital is spherically symmetric, it is simply a sphere. So 1s is a sphere, 2s is also a sphere, but 2s has got a radial node. So, how do we define 2s? 2s is one sphere within another sphere, and in between the two spheres there is a node. That means you will not find electron during that region, and this is what is given in this contour diagram. So, for the 2s orbital you see there is electron distribution at the center, and after that there is a gap where there is, because there is a node, and again electrons are can be found here. So, this is about the radial node. When we talk about 2p orbital, we know that p orbitals have one angular node. You see this is 2py. You can see that in xz plane there is a node. So, there is a lobe above xz plane, there is a lobe below xz plane, but not on the xz plane. So, there is a planar node for 2p, and similarly for 3d orbitals or any d orbitals, you have got two planes along which the nodes are there. So, there are two angular nodes for d orbitals, one angular node for p orbital, and no angular node for s orbitals. Now, the a number of radial nodes is given by n minus l minus 1, a number of angular nodes is simply given by l, and total number of nodes, when you add them up, you will get n minus 1. The question asks, arrange the following orbitals in increasing order of radial nodes, angular nodes, and total nodes. Let us write down this 1s, the orbitals 1s, 2s, 2p, 3s, 3p, 3d, and find out the number of angular nodes. So, since this is s orbital, angular node is 0, again s orbital, angular node is 0, p orbital, angular node is 1, s orbital, angular node is 0, p orbital, angular node is 1, d orbital, angular node is 2. Just by looking at whether s, p, d, I am assigning angular nodes. What about the radial nodes? The radial nodes, 1s is the lowest s orbital, so therefore there is no node. 2s is the second s orbital, so therefore it has got one node. 2p is the lowest p orbital, so therefore it has got no node. 3s is the third s orbital, so therefore it has got two nodes, because I am n minus l minus 1. So, 3p will have one node, 3d is the lowest d orbital, so therefore it has got no radial node. Now, the total number of nodes is obtained when we just add them up. So, when I do this 0, 1, 1, 2, 2, 2. So, you see 0 for 1s, 2s and 2p both have 1 nodes, 3s, 3p, 3d have both all 2 nodes each. So, because number of nodes, total number of nodes is given by n minus 1. So, 3s, 3p, 3d have same value of n, that is 3. So, therefore, total number of nodes is 2. So, total number of nodes depend only on n, angular node depend on only on l, and radial nodes depend on both n and l. Let us look at the next question. This question concerns the effective nuclear charge. If you remember, so we discussed this is the square of the wave function, or the probability distribution of the wave function, corresponding to this diagram corresponds to 1s orbital, this diagram corresponds to 2s orbital of hydrogen atom. What do we see here? We see here that the probability of finding electron in 1s orbital vanishes very quickly. You can see this is beyond 0.2 nanometer, you have almost 0 probability, but when you look at 2s orbitals, you see that the probability of finding the electron even at larger distance between the electron and nucleus is also finite. So, therefore, 2s electrons are found farther from the nucleus, and 1s electrons are found closer to the nucleus. Now, this question asks, among the following pairs of orbitals, which orbital will experience the larger effective nuclear charge? Now, what is effective nuclear charge? So, we have the nucleus which has got protons, and that provides a positive charge environment at the center, and this positive charge of the nucleus holds together the electrons that are around this. Now, if you have more and more number of electrons added to a fixed amount of positive charge, of course, you would see that the electrons will start experiencing less of this nuclear charge or less of this positive charge, because there are many electrons which are competing with each other for the same source of positive charge. So therefore, when you have more number of electrons, not all electrons will experience the nuclear charge to the same extent. This, to the extent to which they will an electron will experience the nuclear charge, is given by this effective nuclear charge. Roughly, when the electron is farther and farther away from the nucleus, of course it is going to experience less of the nuclear charge. So therefore, this effective nuclear charge becomes smaller when the electron is found farther from the nucleus. So now let us compare 1s and 2s. Of course, 2s electron is found farther than the nucleus compared to 1s electron, since 1s orbital is closer to the nucleus. So therefore, the effective nuclear charge of 1s will be greater than the effective nuclear charge of the 2s orbital. Now the other question is 4d and 4f. The argument goes again in the same direction. 4f electron is more diffused, that means it goes farther away from the nucleus compared to 4d, because even if both have same principal quantum number 4, they have two different azimuthal quantum number L. So therefore, 4f, which is more diffused, will experience less of the nuclear charge. So therefore, 4d's nuclear charge will be greater than 4f. And if I compare 3d and 3p, the argument is again same. 3d orbital has L equals 2, which is more diffused compared to the 3p orbitals whose L equals 1. And remember, we are doing this only when the n values or the principal quantum number is same. So comparing 3p and 3d, then I see that 3p will experience more nuclear charge, effective nuclear charge, than 3d. Of course, now we can similarly say that in this case we kept the nuclear charge same, and we said that we compared different orbitals. But suppose if I say aluminum and silicon, both have valence electrons in 3p. So which electron will experience more nuclear charge? Is it aluminum or is it in silicon? So in that case, you have to pay attention to what is the number of positive charges in the aluminum and silicon nuclei. So if the number of positive charges or number of protons are greater in a particular nucleus, and the number of the electron is in the same orbital, in this case both in the same p orbitals with same principal quantum number. So in that case, the greater the positive charge, greater will be the effective nuclear charge, because now more number of positive charges are attracting these electrons. So this is how we do this effective nuclear charge. So in this lecture, we revised the concept of the chapter atomic structure through a number of problems. Of course, you in your textbooks you have many more problems, but I tried to cover all those important concepts that you would need to recall before you can solve all other problems. I hope you would liked these problems, and you would continue to solve other problems based on the inputs that we had in this lecture. Thank you for your attention.